The first topic to consider in our study of dynamics is the topic of kinematics of particles. We're going to talk about particles in the first part of the course and then solid bodies or rigid bodies in the second part of the course. The reason for this is that it's easier to understand some of the basics of dynamics when considering particles and then extend that to solid bodies. I really like these slides. It's one of the reasons I use them, besides the fact that they are slides that are written by the same author as the text, although these are from a later edition of the text. I like them because anything you need in these slides you can click on and get to, and in my course, even on tests, I allow you to use slides for reference if you wish. So this is a really nice tool to have available so you can get a quick overview of what it is you need to use to solve problems. Kinematic relationships are those that are used to help us study and make sense of motion without considering what it is that causes that motion. Now, motion generally will just continue as it is. If you think of a particle just moving in space, it will simply continue moving and never change direction unless some force acts on it. It will also never change its speed unless a force acts on it. But there are things about motion that relate to each other that will allow us to understand and solve motion problems. Now, in dynamics, we not only understand or study kinematics, we also study kinetics. Kinetics are the things that cause motion to change. Now, a lot of people will say that kinetics is the study of what causes motion. I don't think that's a very accurate description. It's more accurate to say kinetics is the study of things that causes changes in motion. So if we consider forces and torques and things such as that, these are things that will cause bodies to change their motion and stop moving as they were before and move in a different manner. But kinematics itself is just the study of how displacement, velocity, acceleration, jerk, all these things relate to each other without considering the forces that cause the motion in the first place, or changes in motion in the first place. Now, particle kinetics includes two main areas. There's rectilinear motion, which all that really means is studying particles that move along straight lines, and then so-called curvilinear motion, motion where the particle does not move along straight lines. There are curves in the path. And sometimes those curves will be in 2 dimensions, sometimes 3 dimensions. In this class, we'll primarily restrict ourselves to the motion along curvilinear paths that are in 2 dimensions, just because they are easier and we're trying to understand the basics of dynamics. In rectilinear motion, a particle just moves along a straight line. It doesn't have any curvature in the path. So we could talk about the position of the particle by defining some origin or coordinate origin on the line from which we could measure the position of the particle. Obviously, the particle could be ahead or behind the coordinate origin. Now, the motion of the particle is known if we know where the particle is at every point in time. Now, this could be expressed as a function. For example, the position equals 6t squared minus t cubed, where t, of course, is time. It could be expressed in the form of a graph, where we know position on the y-axis versus time on the x-axis. And students get confused about this because all of a sudden we have 2 coordinates and it makes them think of 2-dimensional motion. But this really, what I wish is that this graph was rotated 90 degrees, because then our x-coordinate would match the original x-coordinate that we define, and you would understand that we're just talking about how that particle moves along the x-axis with respect to time. Now, what about a particle that is in one position at one time, we'll call that position P, and another position P prime at some later time? Well, then we could talk about the average velocity of that particle, because we would know the distance it's moved over, its change in position, and we would know how much time has elapsed, delta t. And so the so-called average velocity would be delta x divided by delta t. But you have to be careful with this, because it's easy to confuse average velocity with so-called instantaneous velocity. What's the difference between the two? Well, think with me for a minute. What if you had to travel 55 miles and you needed to get there in an hour? Could you get a ticket doing it? Let's say it's a highway and the speed limit's 55 miles an hour. Well, you could, couldn't you, right? Because what you could do is drive 100 or 110 miles an hour for about half of the trip. Well, probably not half, but for some portion of the trip, you could drive very, very fast, and the other portions of the trip drive very, very slow. As a matter of fact, in the limit, you could drive, almost instantaneously, almost up to the new position with a very high speed, and then just drive that little bit of distance that's left in the time that's left. So the average velocity is a very different thing than the instantaneous velocity. In our example, if you had to drive 55 miles in 1 hour and all you knew is the initial and final state of the car, that 1 hour before you were at the original position, 1 hour later you were at the final position, then your average speed, assuming it took you 1 hour to get that 55 miles, your average velocity is simply 55 miles an hour. That does not mean that you obeyed the speed limit, right? Now, you must have gone at least 55 miles an hour along the path to get from one point to the other, but your instantaneous velocity could have certainly been much higher than the speed limit. So instantaneous velocity is the limit as delta t over delta or delta x over delta t approaches 0. And so really we're taking the limit as the denominator approaches 0, because that's when the math blows up and we're dividing by 0. But understand that delta x is also approximating or approaching 0, and yet the ratio between the two is not 0. It is the instantaneous velocity v. Now this really lets us quantify or relate velocity to position. Now, a velocity could be positive, it could be negative, right? It doesn't really matter where the particle's at. The particle could be moving towards the more positive end of the coordinate or towards the more negative end of the coordinate. And so the magnitude of the velocity is referred to as the particle's speed. Now, understand that at this point we realize we need vectors for velocity, right? Because velocity has not only magnitude, but now it has direction. It can be in the positive direction, it can be in the negative direction. And the magnitude of the velocity is referred to as the particle's speed. Now, you got to understand that taking this limit sounds a lot like something you studied in calculus. This looks exactly like a derivative. In fact, it's the definition of a derivative. So what we're really saying is that velocity is the time rate of change of position. That's really what we're saying. So if we have an equation that describes the position of the particle at every point in time, such as what we had before, all we have to do to get the velocity at every point in time is differentiate the position equation with respect to time. So if you do that, 6t squared, or remember t squared, you pull the 2 down, subtract 1 from the exponent, that's just 2t. So 2 times 6 is 12, so we get 12t for the first term. Do the same thing for the next term, pull down the 3, so we get negative 3t, and then take 1 from the exponent, so it's negative 3t squared. And now we have an expression for the velocity as a function of time. And not only could we plot the position of the particle as a function of time, we could plot the velocity as a function of time. And you can see that that's what's been done over there in the graph on the left. Now, what if the particle, we're not so much interested in the position anymore, but we're talking about the velocity. What if the particle has one velocity at one time, and at another later time it has a different velocity? Well, then the velocity has changed, right? And we could talk about the change in velocity, delta v, over how much time it took for that change to occur. So we'd be talking about the average acceleration as delta v divided by delta t. But if we took the limit as delta t went to 0, again, we would get the so-called instantaneous acceleration. Now let's go back to the average acceleration. Let's say that your car is going 20 miles an hour, and right now, and then 3 seconds later it's going, I'm probably going to make the math hard, but let's see. 3 seconds later it's going 80 miles an hour. Alright, well, how much change in velocity was there? Well, let's see, 20 from 80 is 60 miles an hour of change, and it took 3 seconds to do that, right? So it would be 60 divided by 3. Now the acceleration units would be kind of weird because it would be miles per hour per second. It's how many miles per hour of velocity change there were per second. So that would be 20 miles per hour for every second, right? So for every second that went by, your car increased its velocity by 20 miles per hour on average. Now in reality, the car probably accelerated at a much higher rate at the beginning than at the end of that acceleration time. So the instantaneous acceleration would be very different, but the average acceleration would be 20 miles an hour per second. Now you realize we have miles per hour, so we have a time unit in the denominator already, and that's why acceleration becomes length per time, or in other words, length per time squared in dimension. So instantaneous acceleration can be defined as the limit as delta v over delta t, where delta t goes to 0, but average acceleration is a thing as well, right? It's just delta v over delta t. Now the instantaneous acceleration could be positive, okay? So if the instantaneous acceleration is positive, what that means is the velocity is becoming more positive. Now if the velocity was already positive, in other words in the positive coordinate direction, then the velocity will get even bigger. So that was an example of a positive velocity and a positive acceleration. However, it's also possible for the acceleration to be positive while the velocity is negative. So the particle could be moving, in one direction, but it's slowing down. It's starting to accelerate in the opposite direction because the acceleration is positive. Further, it's possible for the velocity to be positive, but the acceleration to be negative. So the particle could be moving in the positive coordinate direction, but a little bit later it's not moving as fast as it was. It has decelerated. It has accelerated in the negative direction. That is also possible. Finally, it is possible that the velocity is in the negative direction and the acceleration is in the negative direction. What that means is that the velocity is going in the negative coordinate direction faster and faster. That's what that would mean. So be careful and do not confuse the direction of velocity with the direction of acceleration. Acceleration and velocity are very different things, and students often confuse the two. Velocity is the rate of change of position with respect to time, whereas acceleration is how quickly the velocity changes with respect to time. Now, again, this is just a derivative, right? Acceleration is the derivative with respect to time of velocity. So, since velocity is itself a derivative, then acceleration is the second derivative of position with respect to time. So if we already have the equation for velocity as a function of time as 12t minus 3t squared, take the derivative one more time with respect to time. I should say take the derivative once more with respect to time. So 12t would become 12, negative 3t squared would become negative 6t, and there's our acceleration expression. So we could now plot the acceleration versus time of this particle. What is true about the kinematics of a particle? The velocity of a particle is always positive. Well, that kind of is the same thing as saying I'm going to define a coordinate for my car that is straightforward, and my car can only go forward. In other words, it can only increase its position along that coordinate axis. Well, I hope not. There's a reverse gear in my car. I hope I can go in reverse. Sometimes I need to. So the velocity of a particle is always positive? No, I don't think so. We could define a coordinate direction and have a particle move in the opposite direction of the positive coordinate. So A doesn't work. The velocity of a particle is equal to the slope of the position time graph. That may be true, but we need to think through that. How about C? If the position of a particle is 0, then the velocity must be 0. Well, no, not necessarily, right? I mean, the particle could be at the origin of the coordinate, but it could already be moving. It could already have some velocity. So particles don't always start off at an origin with 0 velocity. Many times we'll set up problems that way, but that doesn't mean that that's always the case. So C doesn't make sense. If the velocity of a particle is 0, then the acceleration must be 0. Well, no, because think about it. When you first put your car into gear, your car is not moving. Your velocity is 0, but in the next moment your car is moving. In other words, it has velocity, so its velocity has changed. That means at that initial time there must have been some acceleration even though there was no velocity, because the velocity did change. So if the velocity of a particle is 0, that doesn't necessarily mean that the acceleration is 0. So by process of elimination, we've determined that B is the correct answer. But let's justify that. The velocity of a particle is equal to the slope of the position-time graph. Well, what is a slope? A slope is a rate, right? It's a change in one axis by comparison to a change in the other. Well, that's a derivative. So certainly, velocity is the time derivative of the position. So on a position-time graph, velocity would in fact be the slope of that graph. And that is the correct answer. Now from our example of position equals 6t squared minus t cubed, we've already come up with the equations for velocity and acceleration. So the functional relationship of those two things on time. So what are the positions, velocities, and accelerations at a time of 2 seconds? Well, that's pretty easy to figure out because all we really need to do is look at the time axis at 2 seconds, and from the position graph we can read off that the position is 16 meters. From the velocity graph we can read off that the velocity is 12 meters per second, and from the acceleration graph we can read off that the acceleration at 2 seconds is exactly 0. Now notice that the maximum velocity occurs at 2 seconds where the acceleration is 0. Anytime you have a 0 acceleration, that is either a maximum, a local maximum or minimum of the velocity. Similarly, anytime you have a 0 of the velocity, that is a maximum or minimum of position. So if we look at a time of 0 seconds where the velocity is 0, then the position is at 0, right? That's a local minimum. If we look at 4 seconds, well then that is a local maximum of position, and then those are the only two zeros, and of course those yield a local maximum and minimum of position. Now that doesn't mean that the particle couldn't later on go to some other farther away point. It just means that that's a local valley or a local hill is the way I think of it. So what about at 4 seconds? What are the positions, velocities, and times? Well, at 4 seconds you can read off the upper graph the position is 32 meters. You can read off the velocity graph that the velocity is 0. And off of the acceleration graph, the acceleration is negative 12 meters per second squared. So there are the position, velocity, and time, simply reading them from the graphs. Now much of the time the motion of the particle is of course impacted by forces applied to the particle. We'll consider how that works a little bit later. We're not so concerned with that right now. But the point is we will end up with 3 different types or classes of motion. One where the acceleration depends on time, another is where the acceleration is a function of position, and then finally the acceleration could be a function of velocity. Now, once we've applied all the kinetics and all the forces and simplified the equations down, we end up with one of these 3 types of equations. Can you think of any situation where this might occur, where let's say acceleration is a function of position or a function of velocity? Well, in the case of a spring, for example, a spring's force is dependent on how compressed it is. In other words, the force from the spring, which is what will determine acceleration, the force from the spring is a function of position, and acceleration is a function of the force. Therefore, indirectly, the acceleration is a function of position. So that's one example. What about when it's a function of velocity? Well, drag is an example where the force of drag is dependent on velocity, and since acceleration is a function of velocity, or excuse me, is a function of force, well then indirectly the acceleration will be a function of velocity. So these are 2 classic examples where force is dependent on position or on velocity, and there are others as well. Now I've included this just to kind of talk through it. You probably should print it out. I don't know that you'll understand the importance of it at this point, but it's one of those handy slides to have. It's an if-then relationship so that you know what to do. It gives you some guidance. If the acceleration turns out to be a function of time, then the kinematic relationship we're interested in is that acceleration is dv by dt, just the definition of acceleration. And since differential equations by themselves are not typically all that useful, we will have to integrate this equation, and the integral form is on the right. Basically what's happening here is you take the dt from the denominator, move it over to the right hand side, and integrate both the right and left hand sides. And when I first saw this, it blew me away because I had no idea that a derivative, well, I knew it could be written as dv by dt, for example, but I did not think of that as a fraction where I could take the two differential pieces and move one to the other side of the equation. But in fact, you can do that, because even though dv is small and it goes to 0 in the limit, and dt is small and goes to 0 in the limit, this is still just a fraction. So we just moved dt to the other side of the equation, and then what bothered me is that when we integrated both sides of the equation, it seemed like it wasn't fair, right? It's been drilled in you since algebra that you have to do the same thing to both sides of the equation. And so I figured, well, okay, if we integrate the left-hand side with respect to velocity, we better integrate the right-hand side with respect to velocity. And it always bothered me that the limits of integration on the dv term was from some initial velocity to some final velocity, but the limits of integration on the right-hand side of the equation was from the initial time to the final time. And I thought, well, yeah, we're integrating both sides, but the limits are different, so we're not doing the same thing to both sides of the equation. So how does the equation remain true? Well, it helped me to understand that there's a very solid relationship between time 0 and the velocity at that time. What we're really doing is integrating from one state, an initial state, to a final state. So the velocity in the initial state, v0, goes with the time t0 because they're all properties of the initial state of the system. Whereas the final velocity v goes with the final time t. So we are in fact doing the same thing to both sides of the equation. We're just integrating from an initial state to a final state. So everything is still okay, it does work out. Now what if the acceleration is a function of position? Well, what would that look like? Because I mean, after all, the definition of acceleration is dv by dt. So how would we change that? Well, let's rearrange it a little bit, and let's write dt equals dv over a. We'll just move things around algebraically. And then remembering that velocity is equal to dx by dt, well then what we can do is rearrange that to solve for dt as well, and write dt as dx by v. All we're doing is solving for dt. Set the two dt's equal to each other, and you notice we've eliminated time. We've got dv by a, the acceleration, equals dx by v. Rearranging this equation, what we get by putting everything that's alike on one side of the equation, we get v dv on one side, which gets the velocity all on one side, and the acceleration and dx on the other side. Since the acceleration is a function of position, we're getting all the x's on the right hand side. And there is the kinematic relationship between the variables. Now we've already separated out the variables, so we can just put integral signs on the front of each of these and realize that what we need to do is integrate from the initial to the final states on the left hand side from the initial to final velocity, and on the right hand side from the initial to final position. So that's the equation we would use if we find a problem where acceleration is a function of position. What about if acceleration is a function of velocity? Well, in that case there are two different equations we can use, neither of which is necessarily preferred. It just depends on what you have. So acceleration as a function of velocity, instead of writing it as acceleration is dv by dt and thinking of it as acceleration as a function of time, if it's simply a function of velocity, all that changes is where we put the acceleration. Instead of putting it with time, since it's now a function of velocity, we just put it with the velocity dv instead. So we just move the acceleration as a function of velocity to the denominator beneath dv, and move the dt to the other side, and integrate both sides from the initial to final states. Obviously, on the right hand side, since dt is the variable, it's the time, we'll integrate from time 0 to the final time, and on the left hand side we'll integrate from the initial to the final velocity. But that's how we would play that game. What about if we don't have time in there? What if time is not something that in the problem is convenient to work with? Well, you can show that the acceleration as a function of velocity is also v dv by dx. As a matter of fact, let's see, we've already alluded to this somewhere in the slide. I'll let you find it. Oh, there it is. it's ghosted out, unfortunately, where I've put the two dt's together. I've got dv over a equals dx over v. That's this same equation, except where the acceleration is a function of velocity. So it's just rearranged a little bit. Since the acceleration is a function of velocity, what we need to do is get all the velocity terms on one side and all the position terms on the other. So what we'll do is move the dx to the right, pull the acceleration to the left in the denominator, and then switch the sides. I guess just to confuse you, I didn't intend to do that, but hopefully you can move from that differential kinematic relationship to the integrated form on the right hand side. If you can't, don't worry about it. You just need to know the integral forms really on the right hand side, because these are the ones that will be useful to us. So notice on the left hand side we're integrating the position from the initial to final position, and on the right hand side we're integrating from an initial to a final velocity in order to solve this problem and get at the description of motion of position, you know, as a function of whatever it happens to be. It looks like in this case as a function of velocity. So we've managed to integrate it and solve the problem. Now after this slide there are a bunch of example problems I want you to go through. I'm not going to go through them with you. Please go through them on your own. You should have downloaded the slides. You should be going through them with me. And you need to go through these examples because they're good. I've got other example problems that I have recorded for you that I want you to watch as well. But I do like the more concept type questions, so I want to go through this one with you. And so I want you to pause the video and think about the question. The question is that there's a bowling ball dropped from a boat, so it strikes the surface of a lake with a certain speed, 15 feet per second. We're supposed to assume that the ball experiences a downward acceleration, so it moves faster than 15 feet per second even after it enters the water, and the description of the acceleration is 10 minus 0.01 v squared. I'm assuming that all of the units are consistent, so that when we plug in a velocity in feet per second, we'll get out an acceleration in feet per second squared, but let's not worry about that too much right now. When in the water, determine the velocity of the ball when it strikes the bottom of the lake. I wanted to go through this with you to illustrate the selection chart I just showed you. So when the ball strikes the bottom of the lake, what does that mean? Well, notice the bottom of the lake is defined in the problem. If you look over in the image on the left hand side, the bottom of the lake is 30 feet below the surface of the lake. So we know how far, we know something about position. We also have acceleration as a function of velocity. So notice the three things we've got here. We've got velocity, acceleration, which we always have, and we have position. So we better find an equation that involves those three variables. So we can immediately eliminate A and D because those two involve time. Now, could we use some other relationships to get time into the equation? Yes. I mean, obviously velocity is dx by dt. We could go that route, but it would be more difficult. I'm trying to find the fastest, easiest path, so I'm going to eliminate A and D since both of those involve the variable of time. Now don't be confused, you only see dt there explicitly, but that's still the time variable. So we're going to eliminate A and D. What about between C and B? Well, notice that C is useful when the acceleration is a function of position. Well, in our case, we're explicitly given an acceleration equation that is a function of velocity. So we should choose formula B to solve this problem. And that would, if we perform this integration, what we would do is plug in v dv divided by 10 minus 0.01 v squared. We have to break out our calculus books and solve that problem, but it's really not too bad. Once you do that, then you would have the position as a function of the velocity. That's what we would end up with here. So we would have integrated it once, and so then we have a relationship, therefore, between position and velocity. Plug in the position of the bottom of the lake, that would give us the velocity out. So B would be the correct solution strategy in this problem. Now, another question we could ask is, when will the bowling ball start slowing down? In other words, when would it have a negative acceleration? Instead of accelerating, faster and faster going down, it's dropping faster, dropping like a stone, so to speak. When would it start slowing down? When would it be going too fast? Well, the acceleration is equal to 10 minus 0.01 v squared. So if you think about it, what we're saying is, when would the ball have a negative acceleration going upward? Because we've defined a coordinate as positive going downward. When would the ball have a negative acceleration? Well, let's see. We could figure out when it has a zero acceleration, right? So when a is equal to 0, then the term 0.01 v squared must be equal to 10. And of course, if the velocity gets any bigger than that velocity, then the acceleration will certainly be a negative thing, because the second term, the negative 0.01 v squared, would be larger in magnitude than the 10. So that's when the bowling ball would start slowing down. Now, if the bowling ball starts slowing down, then the velocity is going to decrease. Ultimately, what this is asking really is, what is the terminal velocity of the bowling ball in the water? And you can calculate that. Simply set the acceleration to 0. And a reason that might be interesting is because it could turn out that the bowling ball reaches terminal velocity before it reaches the bottom of the pool. And if that's the case, then the equation we had before, where we're using this one, this equation has a big assumption built into it. It assumes that the acceleration just keeps increasing. So what we want to do is break up the problem into two parts. Find the position where the velocity is stagnant, the acceleration is 0, and do the integration from the surface to that point, and then realize that the kinematics have changed, right? The motion has changed, where the ball will simply be moving at a constant velocity from there forward. So we have to be careful with these equations and make sure that we do everything properly. So there's a lot of, in these problems, there's a lot of understanding that the equations we come up with have physical meaning, and they are limited in their description. They only work for times when the assumptions we've based them on are true. So be very careful in using these equations.